Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Intel. We have Johann Lombardi. He is a principal engineer at the company. Johann, welcome to the show today.
Hi, Rich. Thanks for inviting me.
Well, thanks for coming on, Johann. You know, at ISC 19 recently, Intel let out some details about the DAOS file system. And I thought, let's find out more about this. How long have you been working on this, Johann?
I started back on DAOS in 2012. Prior to that, I was mostly working on Lustre with the rest of the team, and we started this project with the Fast Forward DOE project back in 2012. So we have been working on that for more than 6 years now. And 7
More than 6 years. Wow. And just so I understand, I know you're going to get into the details, but does DAOS, does it build on the technology base of Lustre for exascale, or what was the main objective of this project?
Sure. So initially, when we started back in 2012, we thought we could add new semantics on top of Lustre in order to support persistent memory and non-volatile memory storage in general. So we started in 2012 by changing Lustre and adding the DAOS semantics to Lustre. And then we quickly realized that we had some performance issue related to the way we can drive those devices. So we eventually decided in 2015 to rewrite DAOS from scratch as a standalone object store, and there is no dependency on Lustre anymore. We are doing some Lustre integration to provide a smooth migration path to the end users, but that's an independent object store now.
Okay. Well, I'll tell you what, I brought up your slides, Johann. Why don't we go through those, and then we'll do a Q&A at the end. So go ahead.
Sounds good to me. Thanks. So first of all, the title of the presentation is Scale-Out Software-Defined Storage for HPC, Big Data, and AI Convergence. So maybe let me tell a bit more about what I meant with those buzzwords that I'm using there. So the development of parallel file system for HPC have really been driven for the last couple of decades by checkpoint restart use case, right? So really, you do defensive I/O in order to cope with compute not failure. So on a regular basis, you dump the state of the memory to the storage system so that you can make forward progress. And this means that the main use case is really large streaming write, and sometimes when you fail, you restart by reading data. And parallel file system and really been developed with this use case in mind, so large streaming write. But effectively, with the new type of workload, with big data and AI, there's new storage workload that are emerging. So now reads becomes important with AI. Random write and read as well are coming with big data and Spark workload. And really the goal for DAOS is to be able to support all those workload on a single storage tier. Right, so that's really what I meant by HPC, big data, and AI convergence. You can run all the workload on DAOS. And secondly, the storage here is really a central component, right? So this is the place really where all those frameworks can exchange data and communicate. So we are really also looking into advanced storage semantics when HPC, big data, and AI framework can exchange through the storage. So on this slide, we present the architecture of DAOS on the right side and the more conventional storage system on the left side. So parallel file system were really built from the ground up for this drive, and they use the Linux kernel block layer. And the Linux kernel block layer is really optimized for this drive. So it tries to optimize 6, right, with the I/O scheduler, trying to aggregate I/O and coalesce them by delaying in them in hoping to be able to aggregate them and send some large streaming write to the disk drive. And the parallel file system and many have been built on top of this Linux kernel block I/O layer. Similarly, on the network side, we have been using fairly high latency communication, at least compared to MPI. And overall, this architecture has been doing a good job for large streaming write. But as I said before, those new use cases are really emerging. And you can all definitely use 3D NAND and 3D cross-point storage technology with parallel file system. You will get better performance, but you will lose a lot of performance on the table. And more particularly when you start looking into IOPS and I/O latency that are very important for big data and AI. On the right side, that's the new storage architecture that we have been working on. So DAOS stands for Distributed Asynchronous Object Storage, and it is built really from the ground up for non-volatile memory. So it totally bypasses all the Linux kernel I/O. It does not do any system call. It's end-to-end user space. And it is built over 3 building blocks that have been developed by Intel. The first one is persistent memory with the persistent memory development kit, PMDK, which is an NCNIA standard that DAOS uses to store on persistent memory all internal metadata and latency sensitive I/O. Right, so DAOS has 2 different channels. All metadata goes to this PMDK channel and memory interface. Obviously, it will not be cost effective to create a very large capacity solution just with persistent memory. So this is why we combine it with NVMe SSDs to provide bulk capacity. And again, here, we don't use the traditional Linux kernel I/O. We use SPDK, the Storage Performance Development Kit that was developed by Intel, that gives us a user space NVMe driver. So we can issue I/O directly from user space to the SSD without going through the kernel. There is some system call at the beginning to set up the memory address space, but then after that, on the regular I/O path, it goes directly from user space to the SSDs. And at the top, on the communication side, we are using many of the MPI techniques for collective operation and for scalability. So what we did is that we are using this LibFabric interface, which is the same one as what is used by Intel MPI, that gives us very low latency communication and very scalable collective operation as well over the fabric. So that's really this new design, really designed from the ground up for low latency fabric, persistent memory, and NVMe SSDs. And since we bypass all the legacy Linux kernel code, we really cannot support this drive, right? What's good on the left side that we drop is not there any longer on the right side. So we have different type of issue. So you need to be careful with rare leveling, with usage of persistent memory as well. And memory fragmentation, for instance. But all the legacy seek optimization you have for this drive, for instance, is not there. So you cannot use effectively DAOS with this drive. If you need a large capacity tier with this drive, then all parallel file system solutions are probably more appropriate at that time. So this is an example of the 2 major type of deployment that DAOS supports today. On the left side, you have the traditional pooled model where you have dedicated storage rack that run the services. So you have this with Lustre today, and DAOS support the same module. And this is really driven by density at that point. You try to put as much bandwidth and as much capacity you can in a storage rack to limit the number of rack. In this case, you have storage node represented in red here that have on each server you have a mix of persistent memory with Intel Optane persistent memory and NVMe SSDs. And as I said before, DAOS will store all the metadata in persistent memory. The small IOs will go into persistent memory, can be aggregated into larger IOs, and then eventually be migrated to SSDs. If the IO we receive is large enough, we index it into persistent memory, and the data is directly stored on SSDs. This means that we only store the application data on SSDs. And all the small traffic for metadata tracking, space allocation for SSD is stored on persistent memory that is very low latency storage directly connected to the CPU. And we also support the model on the right side, which is more the hyper-converged model, where basically, or disaggregated model that we call as well, when the storage is integrated inside the compute rack. So you can implement it in different ways. You can still have dedicated blade in every storage rack that run the DAOS service, or you can also, in a more hyper-converged way, use container on the compute node, right, and isolate compute from storage by running the DAOS service in a container. So that's the 2 general model. The one on the left side currently is more traditional with HPC system, but we are collaborating with several enterprise partners and customers that are interested in the hyper-converged model, including a cloud service provider. So Looking into the DAOS tier anatomy, DAOS is really not a burst buffer. So what it means is that it's a large capacity tier that provides data protection. In the 1.x version, we will be supporting mostly replication. And in 2.x version, we will be supporting erasure code, right? So it has its own built-in data protection. And unlike burst buffer, DAOS manages its own metadata, which means that we don't need the third-party parallel file system in the back to manage all the POSIX namespace and metadata. So it's a standalone tier. And as represented on this diagram, in order to provide very low latency I/O, DAOS client is effectively just a library that is integrated with the application. Here, run in the same address space as the application, and the data module exposed by the DAOS library is directly integrated with all the traditional data format and I/O middleware library. But I will get back to that later. So on the server side, you have the DAOS service that run, access persistent memory, as I said, for metadata and all small IOs, and store large IO. And for large IO for DAOS is 4K and above or 16K and above, 2 SSDs. And really what is important to understand is that this model is really end-to-end in user space. Again, the IO goes through the library. We send the request to the DAOS service. The DAOS service triggers RDMA directly from the application memory into persistent memory. So file system used to implement 0 copy, but effectively they have 1 copy into DRAM. Here in this case, you have really true 0 copy, right? You copy the data from the application memory directly into persistent memory. We don't even go through DRAM in this case. So large capacity tier, and as I will show at the end of the slide, we have a big customer in the United States that will deploy it at very large scale and very large capacity, and DAOS is going to be is really resilient. So in order to provide very low latency I/O, as I said, we are looking into reusing the same communication middleware as used by MPI. So, but we still want to learn from the software-defined storage and all the interesting work that has been done for ease of deployment and multi-tenancy. So DAOS effectively use 2 different types of communication layer. For the data plane, so when accessing the content of the object store, we use the libfabric, and all communication directly go from the library to the service through this libfabric interface that supports native RDMA with true 0 copy, and it gives us end-to-end user space communication for the network and for the storage with PMDK and SPDK. All communication are non-blocking, which means that the DAOS API also is non-blocking, that allows you to overlap computation with storage, with I/O, right? And we can also reuse all the scalable collective communication that have been built over libfabric. So that's for the data plane. But obviously for storage management, we want to use something that has secured channel built over out-of-band management channel. So we are using gRPC from Google that allows the administrator to manage a DAOS deployment. So you can manage the hardware, upgrade the firmware on the SSDs, deploy new pools, and fetch telemetry data, for instance, through this channel. And here we use a certificate, right, to authenticate the administrator and make sure that no regular user can access this channel. So that's the two different type of network. And on the libfabric side, libfabric works with different providers. So we do support OmniPass today, TCP/IP with the socket provider, Rocky and InfiniBand through the VIRTS provider, and we will be collaborating with ThinkShot support, obviously through libfabric with Cray. And as you may know, AWS recently implemented a EFA provider to support libfabric semantics on AWS. So an important thing we have learned really from software-defined storage, as I said, is multi-tenancy and ease of deployment. So we wanted to have a high-performance storage system that can also support those use cases. So what we have developed really is a new data management module based on the DAOS pool that allows you to manage a pool across multiple nodes that provide a predictable capacity. So in this case here, you have a set of storage nodes. Each of them have persistent memory plus NVMe SSDs. And the administrator will just create a pool. It will specify how many storage nodes this pool should span and how much capacity on each server it wants from persistent memory and from SSDs. And over time, this pool can be resized, so you can provide more capacity on each server, but you can also extend the pool to span more servers. And this pool really is very flexible. As I said here, you can represent it in this slide. You can have pool 1 that spans all the server and has persistent memory as well as NVMe SSDs. Pool 2 that is only restrained to one server, the first storage node, and has only persistent memory. And you can create pools 3, for instance, on 2 storage node that spans that has persistent memory and NVMe SSDs. And as I said, over time, those pools can be resized and extended. And what is interesting to note is that we provide NFS v4 type ACL for those pools, and which means that you can have different access control for each pool and allocate them to different projects and different users. And typical deployment today use one project equals one pool. So one pool per project that will have predictable capacity for each project and isolation. At least in terms of capacity, we don't have isolation in terms of performance yet, but eventually we will implement this type of feature. And this feature is particularly of interest to the second wave of cloud service provider that want to deploy HPC as a service and can just leverage directly this capability to allocate pool to different users, right? And to quickly allocate them and deallocate them, tear down storage in a very efficient manner. So DAOS provide POSIX IO support, and this is implemented as a library that is called libdfs that implement POSIX files and directory on top of libDAOS. And this library can be exposed to the end user through several interfaces. First of all, if we have a framework like Spark, if you use Spark, TensorFlow, MPI-IO, HDF5, for instance, you will be able to directly link libdfs with the application, with this IO middleware of the framework. So transparently, without any change to the application, the middleware or the framework will be linked with libdfs. We will just have to write a small shim layer between the framework and libdfs to directly send all the POSIX call to libdfs. And at that point, the application is using end-to-end user space IO over POSIX without even noticing it. Obviously, not every application uses this type of framework, and there are applications built natively on top of POSIX call, so the libc call and system call. For that, we first provide diffuse daemon that provide a mount point for the DFS that can be used transparently with the application. This diffuse daemon is linked with libdfs that goes through libDAOS and then access the object store. Diffuse provide a smooth migration path, but that's obviously not very performant because we do a lot of communication on the client between the application and the diffuse daemon. That might be good for several use cases where the performance of one single task or rank is not the most important, but still there will be a lot of memory copy between diffuse and the application. So that's why we also provide an interception library that allow us to intercept with LD preload, read and write call from the application and redirect them directly to libdfs so that the application will do end-to-end read-write in user space and without any memory copy. So in order to provide a better performance for regular POSIX IO to application without any change to the application. So all of those things are totally application transparent. We provide POSIX IO as a smooth migration path and for all application, but there is a lot of problem with POSIX IO that we want to address with an extended API. So in this slide, we are representing two use cases. A traditional HPC application that is using a multi-dimensional arrays at the bottom, and at the top, AI analytics application that uses a key value store interface. So when we go through POSIX, you have to serialize your data structure through a POSIX file. At the top, when you have a key value store, you have to manage the offset inside the file because the key and value can have variable lengths. And obviously, a file is a one-dimensional array, so this is very difficult to represent variable size data structure in there. So in this case, for instance, if you want to look up key 3 here in the file, you have to parse all the blocks. And until you find key 3, you have to scan key 1, key 2, value 2, until you find key 3, and then retrieve the value by fetching the size after key 3. And that's not very friendly because you have to scan a lot of data. You have to manage the offset. So when you serialize a file, you have to manage the offset. And this process cannot be done in parallel across many compute nodes. You really have to send everything to one task that will do the file serialization because of this offset management. Similarly, at the bottom, when you have a multi-dimensional array, you have to go through a middleware that exposes usually a very rich API to the application, but at the end, it has to serialize it into a file with managed blocks and so on. And here, what is important to notice is that the cell size of the array might not align properly with the block size. So what is represented here is that you have a lot of fault sharing issue, as we said. For instance, here you have at the bottom, which is highlighted, you have all the blue row with the dark blue row, and you have the in block 3 you have the beginning of the last row that is in the same block as the blue row, which means that every access to block 3 will be serialized at the device level with read modified write, but also at the file system level because blocks are usually aligned on block boundaries. So this will really hurt scalability if the application did not pay attention to properly align its internal data structure over block boundaries. And what you see then is that when it is stored on the storage system, it's totally anonymous block. This will be serialized into a set of blocks, and the storage system has absolutely no idea what it is storing. So this means that it might make decisions in terms of placement that are not appropriate, breaking typically rows or cells or key value store. For instance, the value 2 might be spread across multiple servers, and then you will have to access 2 different servers at the same time to access a small value, for instance. And this totally also prevents in-storage computing because the storage has no idea what is being stored. It just stores the stream of blocks, so there is no ability to do any sort of computation on the storage side, totally independent of the middleware. And in the DAOS API, we are providing a new data model that exports a new type of object. So our object, we provide array object that will allow HPC application to represent their multi-dimensional arrays. We also export natively key value store object that has native support, obviously, for key value store interface, and also multi-level key value store interface. And those objects are represented directly on top of persistent memory. And there is no POSIX serialization required at all if you integrate the middleware or even your application directly with those type of objects. So here in the use case, you have an application, for instance, that wants to do concurrent insert into a key value store API. For POSIX, you have to serialize everything on one rank in order to manage the offset. With DAOS, we will send over the network a key value store insert request. The DAOS server will receive this request, goes through persistent memory. We quickly find where in the tree the insertion should happen, insert it into the B tree, and then store the data directly into SSD. The value in SSD, if it is small, if the value, like in value 3 here, if the value is big, it's stored into SSDs, and if the value is small, it will be latency sensitive, and then it will store into persistent memory. And what is important to note is that so it's very scalable insert, but also fast data retrieving. Because when you want to look up, for instance, key 2, you locate quickly based on the key, what server is in charge of key 2. You send the request to this server. This server look up into persistent memory key 2 and find directly the offset on SSD where the value will be found. Right. So the data access path is significantly reduced, and we don't suffer from all the POSIX serialization constraint at all. And as I said also in this slide, it allows in-storage computing, because now you can run query on the server side by querying keys and values and do some distributed computation over the dataset. Typically at ISC, we've demonstrated I/O latency in the order of 16 microseconds for read and 35 microseconds for write, which is several order of magnitude lower than any existing parallel file systems. So this new API is provided at the DAOS storage engine, representing in red here. And we are working with all I/O middleware and data format out there to integrate this API directly with the middleware so that we can emancipate for all those POSIX serialization constraints, right? And we have done it with HDF5. We have a DAOS HDF5 plugin. We have an MPI I/O driver. We have direct integration of libdfs with Apache Spark, and I have a slide in the coming next. And we're also working to extend this ecosystem. So POSIX I/O is supported, as I said, through libdfs, and we are collaborating with other industry partners to integrate with Veloce, which is a checkpoint restart library developed by Argonne and other DOE labs. Apache Euro, which is a new data format for data exchange for big data, to exchange across Apache Flint, Apache Spark, and so on, it will be very friendly to represent natively on top of the DAOS API, and we really accelerate big data. And obviously TensorFlow and SQL are in our list of I/O middleware that we want to integrate directly with the DAOS API. We also want to integrate with any existing tier, so deploy DAOS smoothly and integrate it with any existing capacity tier that you might have, like Lustre, S3 of HSM. So we are providing a data mover that will be available in Lustre 1.4, DAOS 1.4, sorry, if I remember correctly, where we will be providing that parallel data movement capability at the POSIX level, but also for all those middleware that will be directly integrated with the DAOS API. We have also contributed some changes to Lustre in order to be able to represent DAOS datasets in the Lustre namespace, so that it provides a friendly interface to the user that want to use Lustre and DAOS both at the same time. Just one example of DAOS with big data. So DAOS really aims at providing low latency I/O and high IOPS, which are obviously critical for big data and AI framework. And we have directly integrated the DAOS libraries with Apache Spark, and this is what we demoed at ISC. So the current integration is done through a Hadoop file system abstraction class. So we have integrated libdfs directly with this Hadoop file system abstraction class that allows Spark to directly access DAOS dataset from user space without doing any system call. And we are looking into integration with different type of data model that are already supported by Spark. So the one we are looking into is Apache Euro, as I mentioned, to represent the Apache Euro format on top of DAOS, and that will be directly integrated with Spark. But beyond that, we are also looking into Apache Parquet for SQL support, and also maybe a native DAOS data source that will integrate the DAOS API directly with Spark. Those are work in progress to provide zero copy and end-to-end user space I/O. So at ISC, Intel and Argonne announced that DAOS will be the primary storage for the AURORA system that will be deployed with a very large capacity DAOS tier of 230 petabytes and a bandwidth that will be at least 25 terabyte per second. And we are very excited about this project and working very closely with all the folks at Argonne, a very good relationship, and I'm sure it will help DAOS a lot to prove deployment at very large scale and also smaller scales. So DAOS is open source. It's available on GitHub. There is no secret private repository. Everything is available on GitHub, and all the contribution, all the development happens through pull request, push through GitHub. And this is the public roadmap. So really it's really set up as a community project, open source project. Most of the contribution obviously comes from Intel, but we welcome external contribution to the project. We have a public mailing list and this publicly community roadmap. We are working on a 1.0 version that should be released around the end of 2019 or Q1 2020, depending on how much time it takes to go through all our quality requirement. And then we were shooting for a new release every 6 months. So 1.0 at the end of the year, beginning of next year, 1.2 around the summer of 2020, 1.4, and so on. 1.0 will mostly support replication, and but and 2.x release will be supporting erasure code. That's why we will be likely introducing a layout change at that point. So that's why we changed the major number. We are very engaged now with many partners to do POC and to deploy DAOS at small scales. And we have a lot of collaboration as well for petascale deployment in 2019 and 2020. And DAOS 2.x will be deployed at least on the AURORA system and will be considered exascale ready in the 2021 timeframe and above.
Well, thanks, Johann. This is certainly an impressive effort. I mean, working on this since 2012, I'm curious. No one was talking about TensorFlow back then. How has DAOS evolved since this advent of AI applications has come up? Was there something there already that people thought that this could be used to speed up machine learning and things? Yeah.
Yeah, so DAOS has really been built from the ground up for high IOPS and low latency IO. And machine learning is really a great opportunity for us because this comes with totally new requirements than traditional parallel file system can support. So we are definitely looking deep into those TensorFlow framework and Spark framework and trying to integrate as close as possible to the high component of the framework to deliver the maximum performance and also provide new storage semantics. So since we are not bound to POSIX, we can also look into the needs from those framework and accelerate the storage IO directly into the object store, right? So we are really looking into we can accelerate all those AM framework and IOPS reads. So DAOS was really designed to provide very high bandwidth for reads, which was not necessarily the case for all other parallel file system. And that's typically a requirement that comes from AI and machine learning, right? During those training phase, they can consume a huge amount of data, for instance.
Yeah. Well, was it a challenge in that this persistent memory, DC memory from the Intel Optane hasn't been available for very long, and it's only supported by the new second generation Intel Xeon Scalable processors, right? Was that a challenge for your development team? Is that you're developing this big scale file system for hardware that doesn't exist yet?
Yeah, so we had ways to enable Optane DC persistent memory before, and all the development can also happen with memory, right? Regular memory. Obviously, you cannot reboot the server because you will lose the data. But we also got early access to Optane DC persistent memory that allow us to get the development going.
Yeah. Well, I guess kind of a wrap-up question here, Johann, is certainly this is exciting to see those kind of bandwidth numbers for an exascale system that could be possible with DAOS. What about people that have much smaller systems? Do you think they'll see that kind of breakthrough kind of latency to get their work done from a smaller scale of this?
Oh yes, definitely. So typically the I/O latency, does not depend on scales. We want the I/O latency to stay constant as you increase the number of clients, but the latency number I gave, you will get it with just one rank on one compute node, right? So you will see the acceleration really with any type of application at any scale, right? Obviously, large-scale deployment comes with an own set of challenge, right? You need to make sure that the system can scale and everything that any limits you might have in the file system might overrun. But DAOS definitely provide storage acceleration regardless of the scale on the compute side, for sure.
Wow. Well, hey, Johann, this is very exciting, and I'd really like to thank you once again for coming on the show today.
Thanks, Rich. That was my pleasure.
Well, great. That's it for the Rich Report, folks. Stay tuned for more news and information on high performance computing.